Well, my goodness, thank you so much for the invitation to become a member. I'm thrilled to be able to show you some of the things we've been doing. And as I'm reflecting on being here, I'm thinking, what a sweep of history we are part of. It was not so long ago that our ancestors were a food group for another organism, and we have managed to learn how to farm the entire planet. So that's a kind of accumulation of useful knowledge that Ben Franklin would be amazed at. I think he saw something was coming, but he had no idea how far we could go. So anyway, I want to tell you some of these stories. I want to thank a few people. Of course, people that started my scientific career, my parents. I'll show you a place where I grew up. My thesis advisor, Paul Richards at Berkeley. My postdoc advisor, Pat Thaddeus in New York City at the Goddard Institute there. And my boss at NASA Goddard, Mike Hauser, Bob's brother. So special thanks to them and to my family and all the people that made it possible. But now I want to say a little bit about the telescope that you see there. That's the great James Webb Space Telescope. It is the product of at least 20,000 people. So when you're honoring me, you're actually honoring the collective effort of an immense group of people, and I am not the project manager. So if you want to know how did that happen, it wasn't me. Many special people made that happen. I don't have time to tell you their whole stories. But this is a day of thanks for me and for the entire team, because as you know, when it went up, it was kind of scary, and it worked. So there it is. It's a giant hexagonal mirror up there. It's 21 feet across. We should be using metric units today, okay? 6.5 meters across. It is protected by an umbrella, which you see in gray there. It's a 5-layer sunshade as big as a tennis court. So there it is. I'll tell you a little bit about why we did it and why we care. Let's see if I can make this slide advance. So where did we come from? I think this is a question that I had when I was a child. I still have it. What does we mean? Well, it used to be that you'd say, well, obviously a person is a bag of protoplasm surrounded, and that's the boundary. Honestly, now we know that it's a little more complicated than that, because we are part of an immense network of connections. And that's a very fuzzy thing to define. What is our cosmic history? Well, we astronomers can tell you the story of the atoms, and something of the formation of the objects that we see. We are beginning to work on the question, are we alone? We have an idea of what to do, and we have plans of how to do it. Where are the neighbors? Well, that's to be determined. We read all about them in science fiction stories, but so far as we know, that was imaginary. And it relates to this next question: is life a miracle? As ancient scientists used to think and philosophers used to think, or is it something that will always happen given a chance, which I would call a thermodynamic imperative? Scientific opinion is beginning to shift over towards that one. So maybe it doesn't require divine intervention, although the miracle of life that we see is still rather astonishing, no matter how you think about it. So people want to know, can you go to those other planets? And the answer is, yes, you could go to Mars. And we do not yet have the equipment to bring you back, but we can at least imagine sending you there. Oh, there's a simple reason why we can't easily bring you back. We can't land enough fuel on the surface to bring you up again. So if we're going to go and bring you back, we have to make a manufacturing plant for rocket fuel on Mars. So, well, okay, so we're going to do it the other way. We're going to take pictures and imagination. So I tell people, astronomers see everything twice. First we take a picture, and then we make a movie and a story, and we show you that. So, well, here's the story of the universe, sort of. Extremely compressed version. So we have this story, what we call the Big Bang, which is a really rotten name for the story. Sir Fred Hoyle gave us that name because he didn't like the answer anyway. And we haven't been able to get away from that answer. So just one small word about why it's a terrible name. It makes people think of a firecracker, which is a thing that happens in a pre-existing space and time. But the astronomers have seen the opposite. We see an infinite universe expanding into itself for all time and all places at the same time. So that's not exactly a firecracker. So sorry, Fred, it has misled us all, and we haven't been able to escape it. In Calvin and Hobbes' cartoon story, he said we should call it the horrendous space kablooey, but that didn't stick either. So we have the story of the expanding universe, and it started off and produced all the particles we have. We have quantum mechanics, which is now almost a century old, and we should be planning lots of celebrations for that. That describes how the particles stick together. The idea that every particle is a wave and every wave is a particle is pretty tricky, because you don't quite always know when each one is the right perspective. At any rate, we know it works because here we are, and we are all completely determined by quantum mechanics, even though you don't see it. We know the universe has been unstable in 1,000 different ways. The most fundamental one is that gravity has heated the universe. Gravity was able to slow down the expansion locally, pull things back together, heat them up, make stars, and all of the rest follows from that. So there's too much detail to tell you. It's an astonishing story which is better shown in pictures. I'll show you a few of them. We have learned about information, and now we can say everything that we see here is actually governed by the information content of our DNA, of our environment. It enables the extraordinary complexity that we have. It enables evolution. The information is imperfectly copied from generation to generation. And everything that you see here is the complex result of information being different. So it's not something you could predict. This is what we call an emergent phenomenon. Life is an emergent phenomenon. Even the structure of the Earth is an emergent phenomenon. Otherwise, all of the chemical elements would just be mixed uniformly together. You wouldn't have little items of gold that you could pick up off the ground. So it's all astonishingly complex and wonderful. So we have now understood something about control loops in engineering, stabilizing things. We're going to have a talk about biostasis. Well, in general, we call it homeostasis is the process that keeps you alive, that keeps everything more or less behaving as it was, even as all the atoms are being replaced. My atoms have almost all been replaced, except for my teeth. Pretty much every other atom in my body has been exchanged many times. But I'm still have my same name as that I had when I was born. So how is that? Homeostasis. And it's basically fundamentally unpredictable. So even though you think you know what the election is going to do, you don't. So a little bit about my history. This is where I grew up, got my start as a scientist living on this farm. It's a research farm for Rutgers University in far northwestern New Jersey. If you take Highway 206 north past Newton, this was on the hillside just below the Appalachian Trail. So people don't usually think that New Jersey is anything but flat and 10 miles wide beside the turnpike. But anyway, there was this research farm, and my dad was studying statistics of dairy cows. So when I was 6, I heard that people are made out of cells, and we have chromosomes. And that somehow determines your fate in a way that nobody understands, and we still don't. Now that we didn't even know that it was a double helix then. Now we know there is, and we know how to read the letters, but we don't know what the mechanism is that they control. And even if we did, we probably wouldn't quite know what it meant because it's too dang complicated. Anyway, so I learned science from books, and I was thrilled with astronomy and especially instrument building. So I studied every book I could get on telescopes. So I'm still doing it. I call myself not so much an astronomer as a theoretical instrument builder. So I imagine what I want to have, and I see if I can persuade people to build it. And that's partly because I'm not that good at building it myself. Anyway, my start in life. So a little bit about the history of astronomy. Almost a century ago, Edwin Hubble drew us this graph. It's a graph showing galaxies. Each dot's a galaxy. And the horizontal axis is how far away he thought they are. The vertical axis is how rapidly they're moving away from us. So 1929, we had a plot that shows the expanding universe. It's the first one we had that showed graphically that distant galaxies are running away with a speed roughly proportional to distance. Okay, so the first time you had the idea that there was an age of the universe. If you run the movie backwards, how long does it take before everything is squeezed together? Divide the distance by the speed, you get age, and it's about 2 billion in his numbers, which were wrong. Anyway, we're still having trouble with that scale. But anyway, the current number is about 13.8 billion years of age of the universe. By the way, it was predicted by George Lemaitre, who was a Belgian Catholic priest, a parish priest, as well as having a PhD from MIT. He applied Einstein's equations and said, this is what ought to happen. Einstein said that was ridiculous. Einstein was wrong a few times. But anyway, so now we name this law, this straight line here, the Hubble-Lemaitre law. So what do you do then? Well, you're going to see if this is true. So first we saw that the distant galaxies were running away from us. Then in 1948, it was predicted that the universe should be filled with heat radiation. Alpha and Herman made that prediction, and nobody went to look. But it was exciting things at the time. 300 people came to the thesis defense for Ralph Alpher. Nobody went to look. If somebody had known there was a Nobel Prize waiting, they might have tried harder. That was Nobel Prize came for a work that was done in 1965, published in 65. And so we know there was radiation to find. I was a graduate student in 68, and in 1970 I was looking for a thesis project. Okay, what's there to do at Berkeley? I was a graduate student at Berkeley. Okay, well, some people are going to go measure this cosmic heat radiation. Okay, I'd like to do that. So we measured, and my thesis project, the big part of it, actually failed to function properly on the first flight. So I got a thesis about a non-working project, and I got a job at NASA, where I'd been invited already to work in New York City at the Goddard Institute for Space Studies. I'd been there for about 6 months, and NASA said, we want proposals for new satellite missions. Any ideas? My thesis project failed. We should try it in outer space. So he said, we'll call up our friends. We wrote a thin proposal. This was when that was a good enough thing to get started. And I thought, well, that'll never work. But it did get us started. So 15 years after the napkin sketch, up it went. And it did work because real engineers made sure it would work. And there it is as we imagine it to be in outer space. It had 3 instruments on it. I was in charge of one, the FIRAS instrument, the FIRAS. Mike Hauser was in charge of the Derby instrument, and George Smoot was in charge of the DMR. Anyway, it all worked, and we got a map. The measurements were followed up by 2 other space missions, and so I'll show you our most famous picture. This was the one that made the front pages of newspapers around the world. It's a map of the hot and cold spots in the Big Bang, as we call it. Hot and cold spots, which Stephen Hawking said were really important, like the most important scientific discovery of the century, if not of all time. Okay, well, Steve, I thought that's really nice for you to say that. Well, why is it important? Because we would not be here without those spots, as far as we understand the story of the universe. That is the reason why galaxies can exist. The regions slightly more dense than average were able to slow the expansion under the force of gravity to pull them back in and make galaxies and stars and planets and people, and we're here because of those spots. Behind that, of course, is the story of dark matter, dark energy, and all the other details, and perhaps even quantum gravity, which we won't know about for a long time. So you never know. Anyway, so it was a successful mission. That's the one that the combination of that and the measurement of the spectrum got us the Nobel Prize. And the idea that cosmology was now a precision science. So, okay, what else are you going to do? Build telescopes, take pictures, check out the story of the expanding universe. And after the Hubble was up and was working, finally was repaired after it was not working at first, astronomers knew what to do next. Please build us another telescope that's more powerful and can pick up infrared light, because we couldn't see what we hoped to see even with the great Hubble telescope. And in particular, we were unable to see the formation of the first objects from the Big Bang. So build us this one. And this was now called the James Webb Space Telescope, named after the second administrator of NASA. There's a story there. He was the one who set up the Apollo program, went to Jack Kennedy with a plan, and by the way, on the way to see the president in the taxicab, he doubled the budget request before there was an Excel spreadsheet to tell him no. So he said, I don't think I'd believe those scientists are cautious enough. So he was right. It would have been a disaster if he'd not done that. Anyway, it did work, and within about 8 years, people went from no flights at all practically to landing on the moon. Can you imagine that? He also started up space exploration, space astronomy, probes to Mars and to outer the solar system. So good thing to remember him for. So, okay, here's the telescope. It's a project of Europe and Canada and the United States. Our big contractor is Northrop Grumman Space Systems near LA Airport, and it has on it 4 instruments coming from around the world to take pictures and make spectra. So a spectrum is spread out the light into its colors, and see how bright it is at each different color. It can give you a vast amount of information. To an astronomer, a picture is worth 1,000 words, and a spectrum is worth 1,000 pictures. So we need those things, and we spend most of our observing time on them. I will show you just a little bit more about it. So why would you want to observe infrared light? Lots of different reasons. One of the most dramatic ones is this one. This is the same object, seen with the visible camera on Hubble and the infrared camera. And you see it's a completely different picture because infrared light will go around dust grains in space, and visible light will bounce off. So now the dust cloud that's shown there, which has a star in the middle, is now much more transparent. You can see the star with its jets of material coming out. Second reason, of course, some things aren't hot enough to emit visible light. And the third one is that the most distant universe appears to be running away from us very fast. It means we get infrared light from things that started out at short wavelengths that you could see. So build an infrared telescope to do visible light astronomy at great distances. So that's why we do it this way, and why that telescope is so amazingly complicated and difficult, because we just have to do it. That's the only way to get the information. So what did we see? Here is the first picture we released 2 years ago almost. That went down to the White House for this picture to come out. This is a picture showing a piece of sky where there's almost nothing known. We identified it as a place with almost nothing there. It has a handful of bright stars, which you can see with the spikes sticking out of the images. It has some really, really bright fuzzy galaxies right there in the middle. And they're immensely massive, and it has a lot of little pink things on there, many of which look quite distorted. And those are distorted by Einstein's gravitational lenses. So gravity operates by bending space. Even under Isaac Newton's story, light would be bent by passing near a gravitating object. Einstein said yes, only it's twice as much. So we know how to calculate the properties of those gravitational lenses. So now we have all kinds of funny distorted images of even much more distant, fainter objects, and we have now been able to work out some of their properties. So this was a thrill for astronomers to see. To me, it's beautiful, and it has many secrets in it. The secrets of the very first objects that grew from the expanding universe. Some of those galaxies are magnified by 10 or 100 times, and there once in a while there's a chance alignment of something that's magnified by 1,000 or 10,000 times. So it's a totally astonishing addition to our toolkit, and we're beginning to be able to use it. Some of the things we've seen, well, here are something that we use. This was seen already by previous cameras. This is the Webb telescope picture. It's called the Pillars of Creation. And what you can see here, there's a wind blowing from the top right to the lower left. And why is the wind blowing? Because other stars have already been formed up there, and their energy is coming out and pushing the gaseous material away. By the way, space is not empty. Space is full of stuff. Space is full of hydrogen, helium, other elements mixed up, and dust grains. And you see the dust grains in here in the clouds. And this is a place where stars are being born inside these dust clouds. So why are they being born inside of dust clouds? Because clouds get cold when they're protected from the heat of the other stars. And if they're cold, then the gravity in them can overcome the gas pressure and pull them together to make new stars. So stars are being born inside these cold dust clouds. So it's a formation laboratory to see how stars are being born today. So we don't have the details for you, but obviously when you do understand, there will be many, many, many papers about this object. This is a fascinating picture. This shows a star being born as we speak. What you see in the middle, it looks like a little hamburger bun. In the middle of the hamburger bun is a star, and you cannot see this star because we're looking edge on through the hamburger. The hamburger is the orbiting cloud of dust that's going to be forming planets in there. We presume if you come back in million years, planets will be there and the dust will be gone. So have patience. So obviously a fascinating topic. We know stars are being born with planets all the time. Most stars have planets. About 20% of stars have planets that could be about like Earth, hot enough, heavy enough to hold an atmosphere. We do not know that, but we don't know if they do, but we think they could. So how do you find out if they do? This is one way. Wait for a planet to go in front of its star. If the star has an atmosphere, if the planet has an atmosphere, then the apparent size of this planet depends on the wavelength, according to what the clouds and atmosphere are like. If it's just a little rock, then it's a geometrical object and it's the same size at all wavelengths. So we can now see some evidence of the light that goes through the atmosphere of a planet, see if there is one. So far, the answer is, well, big planets have atmospheres like Jupiter and Saturn. Small planets don't. But that's because we're not looking in the right place yet, and we can't. So now just to give you a little hint of what's coming next, we have other missions, other telescopes being built, as we already have. This is one that was launched last year to look for dark matter and dark energy. This is a project of the Europeans, and we have American pieces in there. And they'll be looking for evidence by way of where are all the galaxies and how fast are they moving. It'll tell you something about dark matter and dark energy. We are finishing up the construction of this one at Vera Rubin Observatory. Vera Rubin was a scientist in Washington, D.C. area at Carnegie DTM. And she was one of the people who worked out the fact that galaxies don't spin right. And they spin too fast. They must be held together by something you can't see. So we call that dark matter. And she showed that it was a universal phenomenon. Almost all galaxies have it. So here's this enormous telescope, and they're going to take a picture of the entire sky that they can see every 3 nights, looking for things that change. Well, they say there will about 10 million things will change every night. You need a lot of graduate students. So actually, the amount of data coming through here is so much that we had to count on continued growth of computer capabilities. Otherwise, it was hopeless to even ever keep up. But we're building it, and we will keep up with the data because they will be telling us things we didn't know about before, things that go flash in the night. We are working at NASA Goddard on finishing up this telescope. It's named for Nancy Grace Roman, who was a friend of mine, was also the head scientist at NASA headquarters for astronomy for many years. And so this is going to look for dark matter, dark energy, and also will carry an instrument to look for planets directly. This is a hard project because stars are bright, planets are faint. So the job is to block out the light of a star so you can see the planet next to it. So they will be doing that. So around 2027, we hope it will go up. They are finishing it up now at Goddard. If you want to come visit, let me know. We are planning ahead, thinking about the Habitable Worlds Observer. This is something designed directly to look for those little Earth-like planets around stars like the Sun. Well, we've got one example in the entire universe where there's an Earth-like planet with the right size and temperature and an atmosphere. So where else are you going to look? Try other stars like the Sun. So this is one of our giant projects coming up in the near future, not near enough. We can't really start on it because we're busy finishing up what we've got. But we do know more or less what to do and roughly how to do it and how big the telescope needs to be. So the astronomers have spoken. This is their top priority for the next big thing. So coming soon, something that'll take a little longer, here programs for the next centuries. What are space and time? Well, we know how to measure them. We don't know what they are, if there is even a meaningful question to say what are they. Are they produced by something else? Well, maybe. Quantum entanglement. People say that. Why does time go forward? Steve Hawking wrote a little book, and I thought, well, you tried to convince me, but I'm not convinced. Even Stephen Hawking couldn't. So why is there more matter than antimatter? They look like they're exact opposites, but why do we have more of one than the other? What are the cosmic dark matter and dark energy? We can measure their effects. We don't know what they are. Is there such a thing as quantum gravity? Is there some way to derive all the laws of physics from some mathematics? Well, we've gotten awfully good at that, but we're not done yet. And are there other universes? Well, some of our stories tell us yes. On the other hand, we wouldn't be able to tell by measurement. So many more questions, and I didn't even put in here, what is consciousness? How did life start? So y'all have a go at it. Thanks. Okay.
Here's some questions. Thank you, John. Questions for John? Don't go away yet.
Okay. Questions?
Yeah, in the back. Someone has a mic? Yeah.
Rich Schiff from Indiana University. Maybe you could comment on what seems a little paradoxical to those of us who aren't astrophysicists. Something is causing all these galaxies to fly apart from each other at ever-increasing rates. And at the same time, gravity is causing these dust clouds and so on to condense and come together into form stars, galaxies, and everything else. Where's the balance between these two things?
Oh, my goodness. Well, the observed balance is that gravity was enough to stop the expansion locally and pull the expanding material back together, but only locally. So here in the solar system, we cannot see any trace of the cosmic expansion. Planets orbit as though there were none. But on the grand scale, when galaxies are millions and millions of light years apart, then you can begin to tell the difference. This expansion thing is a very weak thing.
I think there's a question upstairs.
Oh.
If you
I'm
can
Marvin
identify.
Walters.
Thank you.
Up here.
Yeah.
On the cosmic microwave background, typically the picture you showed there shows the minute temperature differences that were measured. And yet I've read that there's a lot more information that you're able to get out of the CMB due to gravitational waves and some other things. I was wondering if you could explain that to us.
Yeah, I'll give a short story. David Spergel can probably tell you more, but yeah, so he'll tell
Hang
you
on.
more. Anyway, but the cosmic radiation has polarization in it, and you can measure that, and there's more information in that polarization.
Here.
Samir Zeki, University College London. I'm very intrigued by the question, are the laws of physics derivable from some beautiful mathematical assumptions? Would you care to tell us whether you believe that to be true?
I'm not quite sure what the question is. So the laws of physics are things we think are true everywhere, and we do once in a while test them. So, for instance, we want to know if the laws of chemistry have changed. Has the fine structure constant actually a constant, or is it different in the very distant universe, looking back in time? So some of the fundamental constants of nature might not be constant, so we do check it. But so far, they seem to be constant.
Do you hold as correct Dirac's view that you must go by the beauty of an equation in deriving the construction of the universe?
Well, actually, we have a variety of ideas about that early universe, and we just work out which each one tells us. And these days, we manage to adjust all those ideas until they fit the observations. So then it's hard to tell apart. But then you have to say, well, what about the part you couldn't see? Especially the question of, are there other universes? We have a thing called inflation theory that says our universe is produced in a certain way, and that predicts that there could be other universes that we would never know about. And it even says maybe the constants of nature are different in those other universes. So many mysteries, many that we could probably never address.
I think I'll take the prerogative of the moderator and ask you one last question.
Okay.
From the results from the Webb telescope, what's been your biggest surprise so far?
Well, Well, technically, I can't say I'm surprised, but it works perfectly.
So-
But a bigger surprise was how beautiful the images are. So from the very beginning, people said, are the pictures going to be pretty? And I promised them yes. But I didn't know. And now I know that they are so beautiful and they convey so much information. And astronomers are so thrilled. Every year we get 2,000 proposals for what to point the telescope at. So we know it's an immense observational tool and immensely popular. So there's no telling what we're going to discover with this great tool.
Thanks so much.
Thanks for the good question.
Wonderful. Thank you.